So my name is Shuyi Chen, and this is my colleague Rong Rong, and we are from the Uber streaming platform team. Today we are going to present the topic, building Flink as a service platform at Uber. So just some quick facts. We are on 6 continents, 77 countries, and more than 600 cities. And our mission is safer and more reliable transportation for everyone, everywhere. As everybody might already know, Uber's business runs in real time. From the point when you click the button to request a ride or order pizza from the restaurant, everything happens afterwards is real time. You will get real-time notification as soon as the Uber driver arrive at your pickup location, or as soon as the restaurant begin processing your order, or as soon as the Uber driver arrive at the destination or the food get delivered to your doorstep. So to power the real-time business in Uber, we actually heavily invest and use real-time stream processing at Uber. So here is the outline of the talk. First, I'm going to talk about motivation, and then some business use cases, and then I'm going to go a little bit deeper into the Flink as a service platform with Ron, and then finally the conclusion. So first, let's take a look at some of the stream processing challenges at Uber. On the infrastructure side, we are talking about more than a trillion real-time messages per day in Kafka. And we have requirement for at least once processing and exactly once processing. Also, we have requirement on 4-line availability and also 4-line SLA requirement on sub-second latency. What's making the things more complicated is actually we have different infrastructure for running normal backend services and data processing. On the operation side, we have more than 1,000 streaming jobs across Uber running. An individual team can actually own more than 100 streaming jobs. And not to mention the challenge introduced by the multiple data center factors to operate these jobs. And on the productivity side, the challenges are, well, there's a lack of deployment tooling for long-running streaming jobs. So most of the deployment tooling in Uber today is mainly designed for running normal backend services. And also we have to tackle the integration problem in order for the streaming job to run within the Uber ecosystem, like integrating with the logging infrastructure, backend services, storage system, data management, and not to mention monitoring and alerts. And besides the challenges, we also observe a few inefficiency in building a streaming jobs in Uber. To understand that, let's first revisit what's the life cycle of building a streaming job. So the first phase is you have to compose a job. You need to do the business logic that usually include the streaming job and also the backfill. The reason for that you need to do backfill is in case of an outage or maybe a bug is introduced and got deployed into production, you need to reprocess the data using the same logic offline. So that comes the need for the backfill. And then you have to deal with input and output of the streaming job, connecting to, say, Kafka, HDFS, Cassandra, Elasticsearch, MySQL, and etc. for input and outputs. And then also you have to deal with testing, debugging, and the streaming job configurations. So the inefficiency we observe here are mainly first, you have duplicate code for streaming jobs and backfill. And what's making things worse is sometimes people might write the streaming job in Samza, for example, and then write the batch job in Spark, which is making things more complicated. And also, you have redundant code connecting to data source and data sink across different teams. And the next phase is to run the job. In this phase, you have to care about the infrastructure, availability, and also you have to care about deployment, maintenance, monitoring and alerts, logging, and upgrades. On this side, we observe inefficiency here for our developer. They usually have to do manual deployment and manual operation, so making it hard to scale beyond managing a few jobs in production. So to tackle these challenges, we first used Apache Samza in 2015 as the stream processing framework. Apache Samza is a scalable, stream processing engine, and it provides at least one message processing guarantee, and it has managed states and it's fault tolerance. In 2017, we start to adopt Flink. Flink provides all of the above, and also it provides exactly one state processing, which is important for the business use cases related to money and finance. And also it's accurate. And what's more, it provides stream and batch processing within the framework using the dataset and data stream API. So you don't have to split the logic into different framework. So also on top of Flink, we decided to build the Flink as a service platform to address the challenges and inefficiency. The platform provides infrastructure to enable running Flink jobs with 4 lines of availability and provide deep integration of Flink with Uber's backend system. And also enable users to scale production operations up to hundreds of streaming jobs. Next, I'm going to talk about the business use cases. The first use cases is in marketplace for online model update. In marketplaces, there are models like supply or demand to describe the world. And also there's decision engines like pricing, how you price a trip, dispatch, how you dispatch the car, and promotions that act on those models. In order to always construct a real-time view of what's the current world status, the models, our marketplace team used the Flink as a service platform to build real-time Flink jobs that will do online model update so that the decision engine can use the up-to-date models to make decisions. So to hear more about the details, our colleague Xing Zhong is actually going to present the detail about the marketplace usage of Flink in the afternoon talk. And another use case is real-time feature engineering in our WIS platform. So our WIS platform team used Flink to build real-time streaming jobs to compute real-time features to fight payment fraud, promotion abuse, and also account takeover. And here is an overview of the architecture, which the Flink job will first take an event and calling multiple microservices to enrich the event, and then apply custom transformation, and then time window aggregation, and then finally stream to the sync Cassandra, and the query service is provided to query the features in real time for making decisions. Next, I'm going to talk about the architecture of the Flink as a service platform. It will cover 4 parts: infrastructure, application framework, deployment, and the operation by Rong. On the infrastructure side, we pick the infrastructure with 4-line availability such that our developer can build Flink jobs with 4-line availability. So we pick the Uber's deployment system, and also we use Kafka, Hadoop Yarn, and Mesos. And they are both scalable and provide isolations across different teams such that they can run their Flink job in an isolated environment. The next thing is about application framework. To improve the developer efficiency, we provide an application framework that integrates Flink with Uber's backend system. The frameworks include Flink connectors like Cassandra's, HTTP, Kafka, RPC, and MySQL. And also integrate with Uber's metric system to report Flink's runtime metrics in order for our developers to build dashboard, do monitoring and alerts. And also we integrate with the logging infrastructure like ELK and Sentries in order for our developers to debug production issues. So the other challenges we talked about before, it's about deployment. So manual deployment making it difficult for a team to manage beyond a few streaming jobs in production. So enable platform users to scale the deployment to manage streaming jobs. We leverage the existing Uber deployment system. It's highly available, scalable, and used by backend services in Uber. And also, it makes it a central place for the team to manage all the backend services and data processing pipelines in one place. However, that presents challenges. Uber's deployment system is designed specifically to manage backend services running on Mesos. And all our streaming jobs today actually run in a dedicated Hadoop Yarn cluster. So how do we tackle the challenge? Well, the solution is we run a standalone Docker container to manage each Flink job. So the deployment system manages the lifecycle of the Docker container running on Mesos, while the Docker container will manage the lifecycle of the Flink job running on Yarn by coupling their lifecycle. So let's take a deeper look into what the lifecycle looks like. Initially, the Docker client and the Yarn job is stopped. So when the user clicked the start button on the deployment UI, the Docker client will get started on Mesos. And then upon start, the Docker client will submit the Flink job to Yarn. And after that, the Docker client will stay attached to the Flink job and react to changes such as transient failures, such that to make sure their life cycle will be coupled and make sure that Flink job is always running. And when the user clicks the stop button in deployment UI, the Docker client will receive a sick term from the scheduler, and upon sick term, the Docker client will kill the Flink job that is managed on Yarn. And then eventually, the Docker client will get stopped. Also, to enable transparent switch of the resource scheduler, the application framework will hide the detail of the scheduler and provide a deployment API abstraction such that the job can be either deployed in Yarn or Mesos or even maybe Kubernetes in the future. Next, Ron is going to talk about the operation.
Thanks, Shuyi. So with the deployment and the development covers, the next challenge is going to be operation. So let's reiterate what are the challenges on the operation in Uber. First thing is about the scale. We have thousands of streaming jobs running in Uber at the same time, and each team needs to manage up to 100 different jobs, which might be interacting with each other as well. And also, we need to coordinate simultaneous deployments and maintenance over into multiple different data centers. In terms of the complexity of the operation, it's also very unique because we not only need to interact with the Flink job, but also need to interact with the peripheral IOs and microservices like Cassandra and Kafka that it interacts with. And also the operation itself is very business-oriented. For example, like we discussed before, the dispatch use cases, we need to make sure that the calculation of the ETA of a trip is very accurate and robust. So we need a very tight latency SLA. On the very other end, if we are talking about payment transactions and all the other real-time money-related use cases, we need a very, very sensitive SLA on the data loss. So all in all, what our solution here in Uber is to provide an operational automation system called Watchdog. We give it a Watchdog term, but actually it does a lot more. But the basic idea here, we have a decoupled application running for operational automation only on a separated Docker container, which we provide an isolation with the Flink job, but at the same time, because their lifecycle are basically synchronized, we still are tightly coupled with the Flink job itself. So the key idea here is we integrate everything with Uber's metric system, so that all of the metrics from different type of systems, including the Flink job itself, will be piped into the Watchdog system, and it centralizes all the metrics management in order to do operations accordingly. So let's take one examples. So monitoring should be pretty familiar with the audience here. What our solution here is to provide sort of a runtime lifecycle management. So basically, we used the example previously. We take a job, take an input from a Kafka, we do some calculation on a Flink job, and then we dump the data into a Cassandra. So all of three of these systems, including the Yarn computational cluster itself, would basically populate metrics data into our centralized metrics system. And with that information, Watchdog can automatically apply maintenance strategies based on those metrics. For example, in this case, we have Kafka running normal, the Flink job is running healthy, but it's actually experiencing some high Kafka back pressure. At the same time, the most important thing is we detect that the Cassandra is actually basically getting zero data. So the rule engine itself will basically apply that, there might be a transient failure, maybe on the network, maybe on the Cassandra, but we decided to run a strategy to restart the job and try to see if we can mitigate this transient failure. So the other thing is, this is just one example, but from time to time, the Flink jobs can be different from different teams, so we need to provide some type of flexibility on the operation. So what we decided to do is to have a user-defined metrics query, so that user can like basically tailor the metrics to showcase whatever they care the most. In terms of the strategy itself, we do have two different APIs. So the user can either configure to use our rule engine with our built-in strategies, or if that's not enough, they can always use our programmable API to customize their strategies. So another example here is dynamically scaling. So this is not only scaling the Flink job itself, but also scaling with the business. For example, we have an estimate of the inorganic growth of the business, but also sometimes we have like very decisive information, like we are planning to expand into some other cities in the near future. So this basically brings the dynamic scaling a little bit challenging. But all in all, we have some type of like built-in strategies. For example, we can actually scale all the jobs in one of the multi-stage pipelines simultaneously, or we can scale them individually based on the UI or the I/O and the service capacity. For example, if there's a Kafka topic expansion by 2x, we probably need to scale the Flink job by 2x as well. Another thing we need to take a look into here is we want to make sure that the historical data is also taken into consideration, so we don't overreact on spiky traffics on the streaming data. So one example here that we see is there's two jobs consuming from two Kafka topics, doing some aggregation, projection, etc. And there's a downstream streaming job that actually joins them together, doing some correlations. So let's say one of these jobs are over capacity. So what we do here is, let's say we apply the first example, we basically scale the entire pipeline by 2x, and then boom, the Watchdog will basically know that all of this information needs to be applied with the exact same rule. So they would be restarted with more capacity and everything should be resolved. Last but not least, we need to talk about operational management. So cluster maintenance happens a lot in most of the use cases in our production environment, such as OS upgrade, rolling restart, etc., etc. Sometimes HFS is running out of disk space. We need to clean it up. So the idea here is we probably cannot automate everything together, but at least we can provide some type of batch management system to all of Flink jobs, so that when the next time our SIE come and do some maintenance, we can basically apply these default cluster maintenance rules into every single Watchdog that we maintain on that cluster. And then it would basically reduce the operational time and cost. Also, we can avoid human error as much as possible. So all in all, the system is designed to be flexible to handle operational automations, if possible. And if not possible, we at least wanted to make sure that the human intervention can have a powerful automated tool. So the key takeaway here is we build a Flink as a service system in Uber to enable users to develop, to manage, deploy, and operate these Flink applications at scale. So we provide 4.9 availabilities on the infrastructure support. On the application framework, we tightly integrate users' Flink code into Uber's backend system. We manage the deployment system along with our backend service, and then we provide continuous integration on the operational management. Thank you.
Thank you. Yeah, you can take questions.
Yeah. Yes.
Hi, thanks. My question is regarding scaling up.
Mm-hmm.
So you mentioned when you have to scale up, you actually have another service. So that means your service also has to be able to support that. In some way, scaling up by parallelism is different from what you guys are doing, right? So can you talk about, are there any specific constraints that you have to deal with for this case?
Let me rephrase the question. So the question is, does the service, I'm assuming you mentioned the Docker service needs to scale parallel with the Flink job itself, right?
No, the Flink job itself. The Flink job itself, when you run as a parallel mode,
Mm-hmm.
right? So if you just have one service and you have to scale, then you will increase the parallelism, right? But you're saying when you, as an example, if you have more back pressure coming from Kafka, you actually have another replication of your service, right? So in that case, is there any constraint on the Flink job itself that you have to take care of, or is?
I think if I understand the question correctly, if you wanted to dynamically scale up the Flink job itself, we do have managed like a rule engine. So as long as all of the Flink jobs that was managed by their individual Watchdog can take the signal or the exact same rule saying, they are actually belong to the same pipeline, they need to scale up simultaneously, then there shouldn't be an issue for the Flink job to scale up at the same time, as long as the deployment is managed at the same time. Yeah.
Thanks.
No.
So I see that you have Mesos and Yarn, but you run all your Flink jobs in a dedicated Yarn cluster. Why did you choose to not run your Flink jobs on Mesos?
So that is more of a historical reason. So initially we have SAMSA, and then so at that point we decided to run SAMSA on Yang, and yeah, and that's a good point. And actually, there's an effort within Uber. That's why to actually consolidate the resource scheduler for resource efficiency, however, resource efficiency. So that's why we designed the deployment API such that we can actually, it's abstract away from the actual user, so we can switch later.
Okay. Thank you.
You mentioned that you kind of have a requirement that teams also have a backfill support. Is that, you kind of said some of that is in Spark. Do you provide tooling to help support with that, or is it mostly sort of a full Lambda architecture with a batch and kind of a Flink as a speed layer?
Sorry, can you repeat the?
Sure. So you mentioned that teams have to also support backfilling. Do you guys provide tooling or support for that, or is that mostly up to the teams to sort of to have both a batch and a streaming strategy?
So Apache Flink has support for stream and batch processing, right, within the same framework, right? And so that's why we choose to adopt Apache Flink. So with the so on the batch side, we also have tooling actually to support running the schedule and running the batch job. So we actually integrate on the batch side with our in-house workflow scheduler to schedule batch job, because batch has different requirements for streaming, and they are one-off, and they might need to periodically run daily, say for example, to recalculate data. So we actually have a different integration with another the Uber's Uber's workflow scheduler to support batch. Yeah.
Okay.
So in reference to what you said, each application will have its batch jar and its streaming jar, like two different jobs.
Sure, yeah. Let me rephrase the question. The question is, if there's a backfill and a streaming, does each of the jobs have a backfill jar and a streaming jar separately?
No, they're in the same jar.
No.
Yeah.
What is the longevity of your Flink jobs running on this platform? Are they short-lived jobs, or they are the long-running jobs? And there is a link question to that. You mentioned that most of the workflows, they are real-time workflows. I assume there is a part of the jobs which are running offline, but for real-time flows, are you running the Flink jobs as well? And if yes, how does the scaling impact you when you are considering the real-time scenarios which are running onto the Flink this platform?
So let's answer the first question. All of these jobs are running as a long-running application. Okay. So we plan to run them forever, unless there's an upgrades and like continuous integration. So the second question was?
Yeah. Second question was related to the real-time scenarios, because they are long-running jobs. Not because of the real-time scenario. If there is a surge happening into your traffic, then the scaling, for scaling you said you have to stop and restart. Then how does it impact in the real-time scenario? Because both of them, those requirements are impacting each other. Have you seen any challenges there? Does it impact any of the availability or the response time or latency, or?
So the question is, when there's a surge, how do we handle the scaling in traffic, in the input traffic?
Yeah.
Yeah.
And particularly related to the real-time requirements.
Yeah. So actually, that's a good question. Yeah. So we have talked about this previously in some of our other tech talks, and I think one of the challenges we have here is if you wanted to scale it out, let's say by 2x, you need time to allocate the Yarn cluster resources, you need time to upload the jars, restore state from HDFS, so there's definitely a downtime in between, right? So right now what we can do is to minimize this as much as possible, but because Flink, as of right now, I don't think it supports like dynamically swap the job graph, like for example, like one of the component in the job graph. But this is definitely a good discussion we can take into the future.
Yeah, that's a good point. Yeah.
Cool.
Okay,
So I think we have time for one more question. Is there one over there?
I have a question. So which component is responsible for scaling both the Docker and the Flink job?
So the Docker container itself, it does not really lead to, we don't scale it because it's basically just manage the Flink job running on Yarn, and most of the time it's just observing, and so it's on the Flink job, and actually there's a there's a Docker a Watchdog service running within each Docker container that is actually responsible for contacting Yarn for the scaling part.
Mm-hmm.
Okay, I'm sure the two are happy to answer questions on the sides. So please give it up for the two again.
Thanks.